Yeah, so at Event-Driven Perception for Robotics, we're the home of the neuromorphic iCub. So the idea with this, like a long-term goal, is we're looking to do neuromorphic sensing, neuromorphic processing, and neuromorphic actuation. So obviously we have the event-driven cameras, which we've all seen today. We're also looking at things like event-driven touch, and combining with neuromorphic chips for processing, such as low-E here. So that's our end goal. On short term, we're looking to also demonstrate the advantages of event-driven cameras for robotics with vision algorithms. So when we're developing vision algorithms, we're really looking to keep criteria for something that will work on our robots live. So we want the camera running live, we want an algorithm running, and being able to do closed-loop control on the robotics all in one pipeline. So let's say less offline processing. For also this case, we've got moving cameras, we've got moving objects, and we've got unknown speeds that we want to deal with. And if you work with event-driven cameras, you know that this is not always easy. So I'll show you some work that we're working on. Disclaimer, not all of it has all the criteria that I've just said, but we're designing our algorithms in this way to make sure that they're extendable and will eventually run on the robot. And the second half, I'll go through some of these kind of common methods we've used to deal with some challenges we have for all these different methods. So here's a Panda robot doing tracking of this star-shaped object. It's got, you can see the ATIS Gen 3 camera on the end effector there, and the robot's just controlled to keep the star in the middle of the view and also keep it the same size, so we're tracking in 4 dimensions. So here the robot's moving, the shaped object's moving quickly, the camera's moving quickly, and we still need to do the tracking. We've got a cluttered background, which means that we can't just track this object by clustering events, because we get a lot of events coming from the background. So here's a picture of kind of what the camera is seeing. You can see here we're projecting where we're tracking the star-shaped object onto this representation. So this representation here is a surface that's representing where we expect edges in the scene right now. The one on the left just shows you some of what the background is. It's not an easy, let's say, clustering task of events. We really need to look for this shape in the on the surface. And on the right, you can see this is the one where the robot's live control. So you can see here the robot's now moving that star to keep it in the center of the image. And it's moving quite quickly, so we're moving things quite quickly. When Luna gets back to Italy, she needs to strap on an RGB camera at the same time to show that, if you run this kind of thing, this with an RGB camera, that it's going to fail. So we really want to show the event-driven camera's potential for tracking here. Some applications for this kind of tracking, we're looking at doing air hockey with the iCub robot, being able to track the puck moving really quickly on the table. And also looking at some eye tracking. So here some challenges of tracking the iris is that we have blinks and fast-moving saccades. So we want, when the person looks from left to right really quickly, we want to how to use the event cameras to be able to track that kind of motion.
So do you do tracking or you detect just the star?
These ones are tracking. We're assuming the previous position and just looking at an area around that previous state of our target. We can combine that with a detector so we can kind of initialize and recover from failures. We're also doing hybrid frames and events for 6 degree of freedom tracking of objects. So the top right here is the DOPE object detector running on the frame-based camera. It's got a 10 hertz maximum kind of frame rate. So when we move the object quickly, you can see that we're missing a lot of the motions. what we do is we've also got the event camera. We are measuring the velocity of the object with in the events, and combining that in a double, like 2 Kalman filters, one for the velocity and then one to integrate new detections from the dope pose detector. And you can see at the bottom right is the integration of this information. So we're getting not perfect but much smoother tracking of this 6 degree of freedom object. Also looking at doing this kind of 6 degree of freedom state estimation with just events. So here you can see I'm holding this toy car in front of the camera. We've scanned that toy car in with like a 3D to create the 3D mesh of the car, and looking at estimating. So I'm here projecting where we estimate the car in the image plane on the image, and here you can see we're using this same surface as for the other tracking. You can see that at some point, here this is a work in progress. You can see where we start failing, and you can see the car here is estimated in the wrong 60 pose compared to where the events are coming in. Hopefully you managed to see a poster we presented downstairs earlier. So this is work we did on detecting trajectories. The idea being that we want this robot to intercept the bouncing ball. We want to use the event camera to really very quickly, in the first few pixels, we can see the target. We want to be able to have an understanding of where the target will end up, where the robot can intercept the trajectory. And to do this, we've done some training of a LSTM, and from a lot of simulated data with a physics model, and then fine-tuned on some real trajectories. So the typical results we see here is that for this kind of task, the ball's moving fast enough that something like the real sense at 30 hertz, just the tracker failed because there's too much motion blur in the scene to really get a good track of the object. At 60 hertz instead, the RGB camera can track the target. With the event camera, we still get an advantage because we get to see the target like moving in the first few pixels with a much lower latency, and so the LSTM can more quickly understand where it expects the interception point to be, and the robot can move earlier to the interception position. We're also looking at human pose estimation. So also this was the poster, hopefully you caught downstairs. Here we're using this the same representation. We call the EROS, and we've trained MoveNet, so which is a lightweight frame-based network for doing human pose estimation, and we've adapted that to events. And how we've managed to do that is by exploiting really big frame-based data sets. So in a frame-based data set, you've got the ground truth, but you've got a frame. So if we run on the top left, you can see an image with canny edge detector applied to the frames. And on the right there, you can see the output of what we're seeing from EROS. And so because these are not exactly the same, but they're similar enough, what we can do is we can train using like MPII, big frame-based data set, to pre-train our model for like edge-based detection, and then fine-tune on our actual data we're getting from our EROS representation. And this has given us a detector that works well on frames, on the events. So then we've also combined it in a similar way with the 6 degree of freedom object tracking with velocity estimation per joint. So for each joint, we're also estimating at a very high frequency, so 1 kilohertz or more. We can estimate the velocity of that joint, and again, in a Kalman field, to integrate all that together, so we get a 1 kilohertz output of the human pose, combining the MoveNet and the velocity estimation. So this is some of the work we're working on at EDPR, and then the second half I wanted to kind of go through some of the challenges we have for robotics in a more general sense. So event-based cameras have great for robotics, they've got great potential, and some of this comes from the fact that, you know, we communicate just like one event at a time. In reality, it's going to be a packet due to, you know, communication overheads, but we can communicate a small amount of data with a very low latency, and then this data has a high temporal resolution. These are great for robotics because we can do low latency. We can do good tracking because we've got the full track of the object moving. We don't have these frames that are taken at different points in time. But they also bring challenges for robotics. So if you have a high temporal resolution, I'm not sure if, yeah, okay. So here, if you imagine, you also have this ambiguous temporal association. So you might have two events in this girl waving her hand, which are really close spatial temporally. But they're of the hand at two different locations. One, the current location, one, some point in the past where the hand was previously as it was waving. So this is we don't want to tie these two together because they're two different states of the person's hand. On the other hand, the foot hasn't moved for some seconds, 5 seconds or so. There's no much data, but we still want to keep some information about that foot to be able to associate it with the current position of the hand. So we've got a very, very low, very close spatial temporal data here we want to reject, and a very long temporal period here we want to kind of include. So this is one problem we need to solve for robotics when we're using event cameras. Event cameras have a low latency, and that's because we're sending these events at with a small time period. And the downside to this is we don't know how much data is coming through at any point in time. We don't have a frame which is always the same amount of data. So here in this image at the bottom, you can see that the camera is on a robot. It's moved a lot. It's stopped, and then it's moved a lot again. So we got a lot of events and not many events, and then a lot of events. So to keep things real time, we've got a closed loop control with the robot. We need to be able to process this data when a lot of events come in the time that they come in. So we've got to be able to manage to process a lot of events. We can't have to keep things real time, basically. So I'll go through the two solutions that we have there. The first is, I've mentioned a few times, is our EROS, which is a speed-invariant surface. So each element in this 2D array indicates the likelihood that we see a spatial gradient there. That's a bit hard to see, sorry. So this surface is updated asynchronously, so we can push through events at about 10 million events per second, which is pretty nice for our work with robots with the Gen 3 cameras. But if you saw the data set posted today, they're pushing up to 100 million or 200 million events per second, so there's still problems that we need to deal with there. But for our current camera and technology, this is pretty nice. We can update this EROS with 10 million events per second. There's no temporal decay, so we keep persistence. The foot, which is hard to see, will be persistent for the whole time until the foot moves. So these design decisions leave behind some artifacts and some noise, but we hope our algorithm will reject them. So this is also related to what Riyadh was talking about earlier. If I was going to discuss with him, I'd say that possibly he's saying that time is important for these things. but I'd say that possibly some tasks you don't need time. If you're doing recognition of an object, there's not so much time associated with this. But I would say what's interesting would be the order of events. So this surface is updated based on keeping the order of the events very clear, but we don't necessarily care about time. So this is a surface you would use for any applications which don't require time in the task you're trying to do. Velocity estimation, you want to have time in there to be able to estimate the velocity, right? The second thing we do is a hybrid processing architecture with synchronous and asynchronous threads. So basically, to be able to push through 10 million events per second, but then also update a complex algorithm, we need to split into two threads. So the first thread is just our asynchronous event-driven thread, and all it does, read the events and update the surface, giving us, the current estimate of where we expect gradients at this point in time. This is speed-invariant, the way we update it, so we can then, with a second thread, perform our complex vision algorithm, whether it's tracking or camera pose estimation, and we can just run that. I say synchronous here, but really you can just run it as fast as it can possibly go. So here, this thread is not dependent on the data coming in; it's just trying to run as fast as it can. If you've got a really complex algorithm, you might run it 10 hertz, but if you can do maybe a lightweight algorithm, which we do, we try to run this at like 1 kilohertz for our tracking tasks. So in this way, this two-threaded, where we're working things this way, we can get a lot of events through, but also update our algorithm as fast as it can possibly go. The synchronous thread is just going to sample the latest of our surface at the current point in time. So just the context of these solutions for the algorithms or the applications which I showed at the start. So for tracking the either 4DOF or 6DOF, what we get with using the EROS is a consistent appearance. It doesn't matter if the camera is moving or the object's moving. We're getting a consistent appearance of what the object looks like. The hybrid synchronous asynchronous allows us to read a lot of events and still do a 1 kilohertz update, keeping things real time for our closed loop robotics situation. For human pose estimation, we get the EROS is giving us a constant appearance. Like there's a particular case here for human pose estimation, exactly when somebody's like waving their arm, and the legs kind of disappear if you're just using a temporal window or something like that. So this EROS allows us to kind of keep a persistent of limbs that stop moving in this case, allowing the detector to get more information about the foot is still in the same location. It also allowed us to like train our detector on a lot of RGB imagery with all the ground truth and annotations, so it gave us an edge there. It's back? Okay, thanks, Toby. So this one I just threw in. It's a corner detection algorithm. I just threw in to say that you can, using this hybrid structure, synchronous asynchronous, you can still get an asynchronous output. So in this case, the top line is our thread that's doing our asynchronous. And what we do is we update our representation, our surface, and then we immediately, for that single event, we also have a lookup table where we can say, at that point in time, was there a corner here or not? The difficult thing, how do we generate this lookup table saying whether there's a corner there or not? And that happens in our second thread where we're running as fast as possible, generating a lookup table from our surface. So that's just giving us, this second thread is giving us where we expect events to be on our surface, but we can still sample that asynchronously with the events to get an asynchronous output. So conclusions, we've been looking to design event camera algorithms under real closed loop robotic constraints. So we've got these constraints and we want to run it on the robot. I've shown some challenges we get, like the event cameras are great for robotics, but it adds these challenges, so we need to solve them, and we've done so using these two methods. So for then bigger in our group, we're looking at developing, hoping that some of these algorithms that we make that actually work closed loop on a robot can shed some light on how biological algorithms might be working. For example, we know we can implement the EROS in a spiking neural network architecture. It's not so difficult to implement. But an interesting question could be like, is that the location in the brain that persistence is achieved? Is that where kind of that kind of processing is happening, kind of the lower level, or is it something at a higher level? So it would be interesting for us to also look at those kind of questions. Thanks very much.